Okay, here we go again. Starting at 43. When phosphoric acid dissolves in water, the following equilibrium is established, blah, blah, blah. We've got a Ka of this. What is true for the solution containing phosphoric acid? Well, if we look at this, that is a fairly big number for phosphoric acid. So what's true for this is that this reaction goes forward less than it goes backwards. Because remember, if Ka is 1, that means they're equal front and back, going forward and back. If Ka is greater than 1, that means it's going forward. But this reaction is more like this. So it's not quite as small as some, but still it does go backwards more than it goes forward. If that number was a positive 3, then we could say the reaction proceeds forward. We have more product than reactant. But here we're going to say we have more, therefore more reactant than product. Okay. Next one, assuming normal gastric juice is a pH of 2, is primary HCl, what's the concentration of the stomach? So again, we're looking at our box. Remember pH, back and forth to POH, back and forth up and down to H3O plus, and back and forth up and down to OH minus. It does go across the bottom. So this is this lovely thing right here. We are going to be going down. So we're going to be using this equation right here. Okay, so we're going to say the concentration of H plus, or H3O plus, is going to equal 10 to the minus pH. So we're going to go as equal to 10 to the minus 2. So that's the molarity of HCl, because HCl is a strong acid and it will split equally to H plus and Cl minus. So we're able to do that. And that she could have put 1 times 10 to the minus 2 molar, or 1.00, same thing. Next part, given the reaction below, correctly identify the conjugate acid pairs. So first thing I do is say, okay, what's changing from side to side? Well, this one is losing a hydrogen, so these two are going to go together, and these two are going to go together. This one is losing a hydrogen, therefore it is the acid. That makes this the base. And the other side connected to this is the conjugate acid. Sorry, conjugate base. And this is the conjugate acid. So if it was an acid on one side, it becomes a base on the other. If it's a base on one side, it becomes an acid on the other. If it was a weak acid, it becomes a stronger base. If it was a strong acid, it becomes a weaker base. Same thing with the base. If it's a strong base, it becomes a weaker acid. If it was a weak base, then it becomes a stronger base, or stronger acid. You should be able to look at an equation like this and be able to fill in what's missing. So if we have H2SO4, we have water yields HSO4, so that means water has gained a hydrogen, making H3O plus. And of course, anytime we have a charge, it's going to be AQ. We have acetic acid plus something gives hydronium plus the acetate ion. That means we had to have water over here, and of course, it's always liquid. Then over here we have NH3 plus something gives NH4, and that should be NH4 plus, sorry, missed a typo, plus Cl minus. That's a Bronsted-Lowry, so going backwards, Cl minus will gain a hydrogen, becoming HCl, and it's going to be AQ. And this one right here should have been AQ also, not a liquid. All right, so which one has the highest pH? Since they're all H pluses, I'm looking for the biggest numbers. So here, the exponent, look at the biggest exponent, I'm going to have somewhere around a 9. And I can double check that by putting it in my calculator, going minus the log of 0.3 times 10 to the minus 9. That gives me 9.5. Now, there's one here that's really close to that is -8. So I'm going to put that in too because this was 0 point something. So clear 5.3 times, whoops, I forgot to do minus the log of 5.3 times 10 to the -8 . And that gives us 7.27. So I'm just going to do that 0.31 again, minus, whoops, clear all, minus the log of 0.3 times 10 to the -9, close parentheses, 9.5. So this one's going to be my highest pH, D. These others will be a lower pH, and I can double check that by just picking the one below it. I'll do the one above it because I can't read the one below it because I got, anyway, negative log 7.5 times 10 to the -6, bring it down, close parentheses, and that's 5.12. So I can see as my exponent gets smaller, my pH gets lower. So D will be my highest pH. Okay, going on to the next one. What is the molarity of the HCl solution if this solution is needed to titrate this? So first of all, we need to do a C1V1 to figure out what the molarity is. Then I can take the molarity and do the minus the log to get the pH. So a 2 times thing here. Double check 1 OH to 1 H, so I don't have to do the stoichiometry. I can just go to the equation, M1V1 equals M2V2. Going here, V1, M1, V2, and we're looking for M2. So rearranging the equation, M2 is equal to M1V1 divided by V2, plugging in 0.142 molar times 23.3 milliliters divided by 20.0 milliliters. Milliliters cancel, and we end up with, plugging in my calculator, 0.142 times 23.3 divided by 20, and I get 0.1654. I'm going to take one extra significant figure because I'm not to the end, molarity of the HCl. Then I'm going to take, to get the pH, I'm going to take minus the log of that. So negative log of the answer. And I get a pH of very strong acid, 0.78. Okay, which buffer has the highest pH? The HF has Ka of this. So again, we're going to use Henderson-Hasselbalch, and Henderson-Hasselbalch basically says that the pH is equal to the pKa plus the log of the base over the acid. So we know HF is the acid, that would make NaF the base. We can really quickly find Ka, so we can have it for all of the calculations. So negative log of 7.2 times 10 to the -4th, bring it down, parentheses. So Ka here is always going to be 3.14. It sounds like pi. Okay, so now we're just worried about this. So I'm going to say 3.14, 3.14, 3.14, 3.14 plus. So I'm going to set it up like that so I can just write it down real quickly. And I'm going to go through the first one, and it's going to be log of the base, 0.1, divided by the acid, 0.1. Log of 1 is 0, so plus 0, 3.14. Okay, clear. Log of base 0.2 divided by 0.1 equals 0.30. So I'm going to have 3.44. Then I'm going to have clear log of 0.1 divided by 0.2, close parentheses, and I get negative 0.30. So if I add 3.14 to it, I get a 2.84. And then, of course, this one's going to be plus 0 because it's the same number, and the log of 1 is 0. We get 3.14. And it wants the highest pH. Well, the highest pH is B at 3.44. Okay. Going to the next page. So, alkalosis means I'm going to have a pH greater than 7. Acidosis, pH less than 7. Pretty easy. All right, a sample of water from a boy has this much. And when they say water sometimes, anyway, we're just going to go with it. What is true about this water? Well, we can figure out the pH by going negative log of 4.43 times 10 to the negative 4, close parentheses, and we get 3.35. Is this acid, base, or neutral? It's acid. Are hydronium ions or hydroxide ions higher? Well, in an acid, hydronium ions are higher. Hydroxide would be for a base. Can a compound be an acid, a base, or both? Yes. We have water that can act as an acid, giving off H+, or act as a base, giving off OH-. This is called amphoteric. So that substance is amphoteric. Okay, then it talks about some basic stuff here. A base, it has a greater concentration of hydroxide than hydrogen or hydronium ions. In acid, you have more hydronium ions than hydroxide. In a basic solution, I did two basic, I should have said neutral. Neutral, we'll change that to neutral solution, they're equal. Okay, so now we're going to do true and false. In a solution that has 6 times 10 to the 6 molar, the pH is 6. Well, we can check that out real fast by going negative log of 6 times 10 to the negative 6. Bring that thing down. And that's not true because it's 5.22, so this is false. In a solution that has 1 times 10 to the negative 6, the pH is 6. Well, negative log, 1 times any number is that number, so 10 to the negative 6, close parentheses, and it is, so this one is true. Aqueous solutions containing an equal number of moles of this, and this is an example of a buffer. Well, this is a strong acid, and this is its salt. So if we have a strong acid, we don't have a buffer, so this is false. Try and get it so you can read. Sorry, I'll zoom out a little bit. Didn't realize you weren't able to see that. Okay, in the next one, an aqueous solution containing an equal number of moles of this, and this is an example of a buffer. Well, they're one hydrogen away from each other, so that's true. This is a weak acid, so that's good. That means that's a weak base. So, yes, that is true. A solution containing a low concentration of this is a weak acid. Well, HBr is a strong acid. It would be a low concentration, but not a weak one. Weak means it doesn't separate, so this is false. If there are two acids, bring this up a little bit this way. There we go. So you see the rest of it.
Hello, wonderful faculty and staff. Just to let you know, catering company is prepping the meals for you. As soon as that is ready, we will do another all-call and send it out via probably the emergency app. Emails are still taking quite a while, so sit tight. If you like the meal, don't leave yet. We will notify everyone when those are ready.
Okay, so if there are two acids, HA and HB, if HA is a stronger acid than HB, then the conjugate base of HB is stronger than the conjugate acid. Well, if HA is stronger, then the conjugate base of HA is weaker, which is true in that statement. And then if there are two acids, HA and HB, and HA has a stronger acid than HB, then HB dissociates in water to a greater extent than HA. That is not true. It would be HA that would dissociate more because it's a stronger acid, so this one's false. For a solution labeled this, the hydrogen concentration is this. No, because this is a weak acid, so it doesn't dissociate the whole way, so that's false. A solution labeled this, then the hydrogen concentration is, or the hydronium concentration is this. That is true because this is a strong acid, so it totally dissociates. And the last question, conjugate acid pairs, conjugate acid-base pairs differ by the resonance of a proton. Yes, basically that means by a proton, so true. All right, and that is it. So if you have any other questions, please feel free to email me, and I will try and get that done as soon as possible. I'm trying to look at you. I've opened up the discussion boards on your Canvas, so you can talk to me that way too.